Welcome everybody. It is office hours time again. If it looks like I've been crying and I'm a bit croaky, I literally just about choked on an Easter egg. So excuse me, I should have been eating chocolate before the session started. Welcome along. We have a special treat tonight, and I don't want to take up any one of my other speakers' time. So I'm just going to go through a few quick slides. Hopefully you can hear and see me fine. Sing out in the chat line if you can't. Let me fire up a few quick slides and then we'll get straight into our special guest tonight. Okay, getting in touch with me is easy. It's linktree/Connor. You can get my Twitter feed, Facebook, Instagram, etc. All that kind of stuff very, very easily. Let's cover off a few bits and pieces, a few administrative tasks, and then we'll jump straight into the main event. I'll be speaking at the Greater Lakes Conference in May. If you want to get along to that, I'm pretty sure it's free, but the most important thing is rather than having small sessions, we're having big workshop-based things this time. So I'm doing a 2-hour workshop on, I think it might be SQL performance tuning, but a lot of the components of this event are workshops as opposed to small sessions. So you get a lot of more getting your hands dirty kind of stuff. Our Dev Live series for the Oracle, which we've been doing for the last year now, once a month. There's Java, machine learning, etc. We've wrapped back around to the first topic, which is all things database. So I'll be doing a talk in that event. So you can see that it's at several time zones. The nice thing with this is, once again, after the session, we have a full 90-minute hands-on lab that you can actually work through some of the actual things that we talk about in each session. And one little promo for myself, the podcast. I started the podcast in January. That's now live and up and going. We've just released the latest episode, which is Every Index is a Bug. And if you're interested in why I think every index is a bug, check out that. You can just go to conmcdonald.podbean.com. Normally on office hours, we go through your questions and we cover them off. But today we have a very special session, which was once again motivated by you, the user community. Last month, I did a little tiny question on something about Ash timestamps, and someone said, could we get some more information on Ash? That was one of the things that came in on the chat. So what did I do? I reached out to the man. The man, you know, this man has forgotten more about Ash than most people know. So by way of introduction, this is John Beresniewicz. He's the architect of so many things related to active session history, performance, enterprise management, performance pages. If it's got related to performance, he's pretty much had a finger in dabbling with it in his time at Oracle. And that time at Oracle goes a long way back. That's me and John there. I think that's 2001, maybe 2002. I'm not sure.
That is scary.
That's right, but it's a while ago. It's a while ago. But having said that, without further ado, I will stop my video and stop my share, and I'll hand you over to John. Feel free to put your questions in the chat line. I'll keep an eye on the chat line, and if you see anything I think that I should interrupt John for, I'll jump in there, or I'll try even answer myself. Over to you, John. The platform is yours.
All right. So, well, that's me. That's my LinkedIn profile, and it's not leading this presentation because I'm a social network climber or something. But basically, at that profile, you can find links to slide shares of these two presentations. Connor kind of suggested I do the presentation on the right, which I did at Rocky Mountain User Group in 2019, basically the week before the pandemic broke loose. And the other one, as you can see, is from Rocky Mountain Oracle User Group in 2014. And in that one, I kind of tried to capture, you know, we had done many presentations about Ash over the years, starting with database 10G, circa 2003, when we had to really start talking about Diag tuning, what we call Diag Tuning Pack, what we then called just database manageability. Diag Tuning Pack were sort of twins that were formed out of a unified whole called database manageability that came out with Oracle 10G. Anyway, you know, these two presentations, kind of long, kind of, you know, kind of old, kind of long. So instead, what we got here today is what I call Ash Mash. So I went back through these presentations and kind of cherry picked what I thought were some of the better slides and tried to knit those together into a relatively coherent, hopefully, story that we'll tell today. And in this, being that this is office hours, which I remember from college days, I'm going to play the role of Professor JB. Okay, so topics, not an agenda. We don't have an agenda. We have topics. It's office hours. So we're going to talk about DB time and average active sessions. Very important core concepts. Measuring DB time, very brief discussion of time model. Then the ASH mechanism. We're going to see a slide that dates back to probably 2005. ASH math, the essential way that we normally use ASH. ASH is not limited to what I'll talk about in terms of its utility. In fact, there's lots of kind of advanced uses for ASH, but we'll stick to the basics here. You know, once you understand the basics, then you can start reasoning about the more advanced things. And then hopefully we'll get to my favorite thing, which is ASH Viz, right? We're going to see a lot of Viz, but not like what we'll see at the end if we get there. All right, DB time. So this is what I call my elevator pitch about DB time. Database time, DB time, is the fundamental metric underlying Oracle database performance tuning methods and tools since Oracle 10G. DB time is literally the amount of elapsed time user sessions spend executing database calls, and it increases in direct proportion to both call latency, response time, and call volume. In other words, if we're measuring time that calls take in the database and calls start taking longer, then database time increases, right? And if calls don't take longer, but we process more of them per second, call volume, then DB time increases also. And we decompose DB time fundamentally into two classes of time, either working on the CPU or waiting to work on the CPU, right? In other words, DB time is all about either working or trying to do work. And twiddling your thumbs, not asking the database a question, does not count as DB time. And normally we see that manifest in the database as a wait event called SQLnet message from client. Right? That means database is waiting for you to tell it something, to do something, right? But we don't consider that DB time. DB CPU and wait time. Okay, so we'll talk about DB CPU and wait time. But basically, that's how we decompose DB time, either CPU time or wait time. And basically, tuning performance, improving performance means doing the same amount of work in less time, right? If you run the 100-yard dash in 10 seconds, you're a lot better than me because I can't run it in probably less than 20 seconds. So doing the same work in less time is improving performance. So we measure DB time primarily from a performance tuning angle so we can shrink it. We can figure out how to shrink it without diminishing the amount of work we accomplish. That's improving performance. Idle time is also an important class of user time, and I kind of mentioned it, right? So this is a slide from a previous presentation, and these little things that will slide in are sort of my little, anecdotal remark about that slide. Okay, so this is from the older presentation. I just cut and paste out of a PDF. So database time and active sessions, right? So we started to talk about it. Database time is total time spent by sessions in the database server actively working on CPU or actively waiting. So meaning like if I'm waiting for a block, a data block in order to compute something on the data that's in that block, but I have to do IO. Well, I wait for IO, and then when the data block is in my control, then I can go and process it. So waiting actively is different from just waiting without any idea. So non-idle wait is what we call that. So active sessions are the number of sessions that are actually active in the database at any particular time. Okay, seems clear enough. And then this all-important concept, average active sessions. Well, how do we compute that? Before we think about the meaning of it, let's just look at the definition. It's the amount of database time divided by the amount of lapse time. Now, what does that mean? Database time is always measured between some beginning time and some ending time. How much time accumulated in the database from time t0 to time t1. And the elapsed time between t0 and t1 is the denominator in this equation, okay? So anytime we compute something and divide it by an elapsed time, we're computing a rate, right? Like a rate of increase. So DB time, average active sessions, in other words, is the velocity of DB time. It's the rate of change of DB time over time, right? It's the rate at which DB time is accumulating. And that's a very important thing to understand. Because of this, which is that because average active sessions is the rate of change of DB time over time, right? And you can sort of see it represented in mathy form here, the way we did in calculus. Active sessions is a function of time. It's the rate of change of DB time over time. Well, then we can integrate that, right? We can integrate the derivative to compute DB time, right? So active sessions is actually the derivative of the DB time function. So what does that mean? When we graph the active session function, right, we're graph the area under the curve, which we all understand to be the integral, right, is the DB time, okay? And that's exactly why the performance page and the top activity page are literally pictures of DB time, because the area under the curve is exactly equal to the DB time. We're plotting the derivative of DB time. So the area, the integral, is the DB time. All right, why am I not going down here? It's calculus. I knew something was supposed to happen. So this is a weird concept, but we'll talk about it. What really, whose time is DB time, right? Well, it's really the time of the clients of the database. They're the ones waiting for the calls to complete so they can, do the next thing, process the next order, serve the next customer. So it's really enterprise time, right? And the key point here is it's not the database's time, it's your time. And that's why I say it's fungible, right? It's interchangeable, right? Your time spent here and your time spent there. Well, if I save time there, I can spend more time there, right? So it's a fungible quantity. And that's precisely the argument on which this visualization is based, which we called the enterprise load map. It was the first time a tree map ever appeared in any Oracle product, to my knowledge. And this is literally a picture of the total average active sessions in an enterprise composed of looking like several hundred databases. Every square, well, they're not all squares, but every rectangle in the tree map represents a different database. And the rectangles are sized by the average active sessions, the rate at which DB time is accumulating. So this is actually a picture of the rate at which DB time is accumulating across the entire enterprise, right? Now, and it's sized by the average active sessions. In other words, the busiest database, the one with the most activity, has got the largest square, and it's called scribble, scribble, scribble .world, right? It's got 169 average active sessions. The next largest one is 19, okay? So King Kong in this environment, in this enterprise, King Kong is an order of magnitude larger than any other database. Even though they've got hundreds of databases, King Kong is King Kong, right? All right, let's talk about measuring DB time. How are we doing on time, Connor? Am I flying or am I slow?
We're at 15 minutes past the hour, so hopefully you're approximately a quarter of the way through. Oh no, a little less than that.
All right, we'll have time for questions. That's good. So we measure DB time. okay? And one of the main forms of instrumentation for measuring dB time we call the time model. And you can see time model data in these. This is now in the days of PDB, CDB, a lot of these AWR and $B tables have new versions, which I haven't incorporated here. But sys time model and DBA hist, the AWR capture of sys time model, and also sysmetric history all have what we call time model instrumentation. And these are basically stopwatches built into the code path, right? And the most important ones are the dB time stopwatch. So when a call comes in, a stopwatch starts, and when the call completes, a stopwatch stops. And the delta between those two, we call total dB time for that call. And then there's other stopwatches inside that call that try to time other operations. But that outer call, that overall dB time call, is one of the most important measures that the time model captures. And the other critical measure that the time model captures is dB CPU. Okay, so dB CPU is not timed by the code path. dB CPU is actually fetched from the operating system. So it represents real CPU consumed. As opposed to if I tried to time things and I end up on the run queue, well, that time is going to add to the overall time, but that's not time spent really on the CPU, right? So that's the difference between dB CPU from time model and other and ASH estimates, for instance, of CPU. ASH estimates of CPU usage can be polluted by run queue time, or distorted is a better word. Distorted meaning the number gets wrong. Whereas in time model, dB CPU is actually coming from the operating system and represents real cycles consumed. That's an important thing to know. So we also have some instrumentation called the weight model. And a lot of people are kind of familiar with this. This is what, weight events, right? And, back in the, back in the late 90s and early 2000s, weight event tuning became very, very hip, right? That was sort of a very cool thing. And it all kind of started quite a long time ago in version 7. And the weight model actually preceded the time model. Time model, as we know it, came out with 10G, but the weight model, we started timing weight events in Oracle as early as version 7. So that's interesting. But weight model, in my assessment, when we're measuring wait time, we're measuring a piece of dB time. So I consider it part of the dB time instrumentation. And we usually split dB CPU and then IO weight as a subclass of all weights, and then all other weights. This sort of breakdown between CPU, IO, and any other weight is one of the sort of fundamental breakdowns that we often do, like say in enterprise manager pages or other areas where we would visualize database activity. If we don't want a very fine-grained view, we just split it up into CPU, IO, and weight, which is a very useful way to summarize what's happening. And this all started a long time ago. All of this sort of dB time stuff, really, I date back to a paper by a gentleman named Anyo Kolp, ex-Oracle employee, wrote a paper called YAP, which was, I think, yet another performance profiler. I'm not sure, but I think that's what YAP stood for. And it basically described, tuning using weight events and shrinking weight event time and figuring out why things were waiting and reducing the time spent doing things from that, using that methodology. Okay, so sounds like we got, the dB time thing covered, right? So why do we need ASH, right? What's up with ASH? This fancy thing that nobody understands. Well, the motivation for ASH and 10G was to have a performance diagnostics tool that was always on, had a historical record for forensic purposes of what happened, had fine level of granularity, and that's a key thing, right? And avoids the averaging effects of coarse time granularity. So that's why we want fine granularity. When you're talking about, for instance, AWR snapshots, typically an AWR snapshot averages all activity over an entire hour, right? And it's not going to tell you about the 5 minutes of hell that you went through, right, in the middle of the hour, because that gets averaged out with all of the, okay time during the rest of the hour. So ASH is really principally about fine granularity, both in the time dimension and also, fine granularity in the time dimension, and then wide level of coverage across many other dimensions. And we're going to see that in a second. And ASH needs to be very efficient and robust. It doesn't do any latching, no locking. It needs to work well, even when the system is under duress, right? That's when you really want to know what's going on performance-wise. You can't have your go-to performance tool falling over when performance gets rough, right? So these are all requirements. And the reason also for ASH is you can't time everything, right? So you want to have insights into a lot more things that are going on in the database than you can possibly have stopwatches for, right? And so ASH, what we do in ASH is, rather than time everything that everybody is doing, we basically take pictures of what everybody's doing every second. And then we use those pictures to assemble an overall picture of what's happening, and also to estimate how long things are taking, right? If I have a video of somebody walking across the street and I know the frame rate of the video is 30 frames per second, and I can tell how long it took to cross the street from the video. I didn't need to have a stopwatch when they started crossing the street and they stopped it. If I have a video and I know the frame rate of the video, I can tell how long, because I can just count frames. And I know it's 30 frames per second, and it's like, 30 million frames. Well, it took a million seconds or whatever to cross the street. All right, let's keep going. ASH mechanism. I'm not going to talk a lot about this. This slide probably goes back to like 2004 or something, but it describes mostly the data structures involved with ASH. And actually, I want to do a better picture, or maybe an alternate picture of really the processes that are involved with ASH, because that's, to me, almost more important. But the main mechanism for ASH is this circular buffer in the SGA. And I don't know, that 2 megabytes per CPU parenthetical remark probably is a little bit out of date. But the circular buffer is maintained by this dedicated process called MMonLite, MMNL. And what MMonLite does is, well, let's step back for a second. When sessions do work in the database, right, they keep track of all kinds of stuff about what they're doing in something called a session state object, okay? So it's basically exactly what you would think. It's a database, it's an object or an area of memory in the SGA that's dedicated to a specific session, and where that session keeps all kinds of information about its current state in the database. What SQL is it executing? What wait event is it waiting on? If it's an IO event, what block is it trying to get? All kinds of information about what that session is up to. And it gets changed all the time, right? The session stops parsing and starts executing a SQL. Lots of little things change, right? So session state objects are very dynamic. As sessions do things in the database, session state objects get updated by those sessions in all kinds of ways at very rapid rate, potentially. Now, what does MMonLite do? MMonLite wakes up every second. And when I say every second, I don't mean on the second, right? I mean, MMonLite just hews to a 1 second sampling rate as well as she can. So what does MMonLite do? MMonLite wakes up once per second, and walks the list of session state objects. There's a linked list in the SGA that connects all the session state objects to each other. So you can start at the beginning and go from one to the next, to the next, to the next, right? And that's what monlight does. And monlight does at every session says, hey, is this session active? Oh, is it active? It is active. Oh, let me write all this information. Let's write all this session state information into this circular buffer and then go to the next session. So it has to go very fast because we really want this to be like a snapshot in time, even though it has to go sequentially through all sessions and, you know, do this decision and do this writing. It has to happen very fast and in a non-interfering way. So it can't try to latch or lock, you know, session state objects while it's copying data, even though this data is very active. And there's some ingenious mechanisms in ASH to make sure that, let's say, while it was copying data from the session state object, some of that data changed, let's say from the beginning of the copy operation to the end of the copy operation, which is a possibility. It protects itself against doing that. Anyway, I won't talk more about this. Oh, very ingenious thing here. This business about the writer going in one direction and the readers going the opposite way. That's a very nice way that ASH keeps readers and writers from ever interfering with each other. The writer is writing to the front of the circular buffer, and anybody that wants to read ASH actually starts at the current write point and goes backwards. And then when it meets the writer again, well, that's all there is, right? So it starts where the writer is and then goes the opposite way until it crosses. And that's when you've read the entire buffer, because now you were going to older rows and then all of a sudden you're hit a new row. Well, that's where it ends for you. Anyway, it's a very ingenious thing. Okay, the fix-up. So the fix-up is also a very unique feature of ASH. You know, there's sort of you could call them poor man's ASH, I think out there, which, you can just sort of query $session regularly and stuff it into your own table and say, hey, I got my own ASH, right? And, that's not a bad thing to do, really. But the fix-up is a really unique and important mechanism. So what is that? Well, when ASH samples, a lot of information that you're really interested in may not be available. And one of those would be, let's say, if you're sampling an event, if you're sampling a session that's waiting in a wait event, one thing you'd really like to know is how long did that wait event last, right? Now, when the sample happens, it's still waiting. You don't know when the end is, so you can't possibly know what the time waited is. But the session eventually does know what the time waited is, okay? So there's a mechanism called the fix-up mechanism where when ASH samples a session, any of the columns that might not be known, like time waited for a wait event, get put on, basically a callback gets registered with the session that says, hey, when you know this, exercise this callback and fill in this value. And then monlight picks up those fixed up values, the time waited after the session stopped, after the session stops waiting, it knows what the time waited was. It actually posts that to this little fix up list. And then monlight, in addition to sampling, also processes the fix-up list. So in that way, monlight is the only thing that touches the ASH buffer, right? It's the only thing that can write to the ASH buffer. So it's an ingenious little mechanism that allows us to do these fix-ups, which are pretty important, like plan hash values. If the SQL is still being optimized and plan hash is not known, well, then it'd be nice if we could just update the ASH samples with the plan hash that was causing all this CPU usage, let's say. Anyway, maybe that was a little too long for that. Oh, the last point is kind of important. So if you just query ASH, I didn't really mention, well, I did mention this. When you just query ASH, you start at the very most recent ASH rows and work backwards, right? And so there's a slight danger there if you're relying on if you're really looking at the first few, like if you're selecting only the last 5 seconds of ash, you're going to get unfixed up rows. Not all of them, but very possibly some of them. And so depending on what you're trying to do, you have to worry about, am I depending on, am I assuming things are the case that may not be the case? In other words, that all the rows I've selected are completely fixed up. So what's in ash? Well, I'm not going to spend a lot of time here, but these are just column names from active session history, and we call them dimensions, right? Why do we call these dimensions? Well, we basically call these dimensions because ash is a giant fact table, and that's how we generally use ash, as a giant fact table. And what do you do with a fact table? Well, you aggregate across, you aggregate the fact across various combinations of dimensions, right? You kind of count and group by, right? And these are all the dimensions you can group by. And these are not all the dimensions. These are just some examples of dimensions. There's, I think in recent versions of ash, there's probably over 100 columns. These particular columns are ones that you probably want to avoid. They were introduced with SQL monitoring, specifically for SQL monitoring purposes, but the ones in red are actually pretty useful. You can just go into ash and very quickly find out which session and which SQL were responsible for allocating the most PGA or the most temp space with a very simple query, right? And that's pretty cool. Okay, the bit vector. The bit vector is another ingenious mechanism in ash. And the way it appears in $V active session history is as a bunch of these columns that say in underscore something or other, in connection management, in hard parse, in bind, in sequence load. And they're all varchar2 ones because they're Booleans, right? And so these things are actually part of an ingenious mechanism whereby we use ash to estimate time spent on very low latency operations for which it would be impossible or it would be impractical to actually time those operations, right? And so like, binding variables should be an extremely low latency operation. And, putting timer calls around binds would actually, vastly blow up the amount of CPU time it took to do binds, right? Because taking timestamps would be a significant amount of the total work. So instead of that, what we do in ash is, turning timers on and off is relatively expensive, but setting a bit on and off is very cheap. So there's in the session state object, there's what we call the bit vector, and various operations have dedicated bits in the bit vector. And when the session is in that operation, let's say it's trying to bind variables, it just flips the bit. And then when it's done, it flips the bit back, right? Well, that's a lot less overhead than taking a timestamp. It's very minimal, right? And so when MON Lite, the ash sampler comes along, it samples the bit vector, and it can tell whether the session was in a bind or not, or was it parsing or in a hard parse. All these bit vector columns. So, and then we use those bit vectors to estimate time using ash math, which is what we're going to talk about now. How's the time? Cruising?
We're about 9:33, so you're doing well, John. You're rolling perfectly.
I'm rolling. Okay, good. I'm glad I'm rolling. All right, so this is ash math, right? So what is ash math? Ash math is how we estimate DB time using ash, right? Ash samples. And the basic equation is very simple. We count ash samples and we equate that to seconds of DB time, right? So ash is a fact table. What is the fact that we're looking at? The fact is 1 second of session time in the database. Each row in ash stands for 1 second of DB time. Well, what was that? What was, what do you mean it stands for 1 second of DB time? I mean, obviously between the last sample and this sample, it's not like the session was only doing whatever is represented by the sample, right? Because the session things change, right? 1 second is a long time in a database. But in aggregate, the samples kind of add up to the overall activity in a very close way. And that's really what the magic of DB time is. So we kind of use ASH. We decompose DB time. In other words, we could just add up all the ASH samples and say, well, there was 8 million hours of DB time. Yeah, that's not so interesting. It's like, okay, how was that 8 million hours split up by SQL ID? Of those 8 million hours, the 3 million hours that were spent doing IO, what objects were they doing IO on, right? That's what we can use ASH on. We can divide DB time up in all kinds of ways that help us analyze what was going on in the database. So this SQL here basically will show you, it will show basically, let's see, average active sessions by SQL ID by minute, right? So you could track minute by minute which SQL IDs were doing the most work in the database using that query. Okie dokie. So in the product, that's what this is. This is ASH math, right? This is a pretty old screenshot, but it looks very similar to stuff we have now, right? And in the top chart up here, we're decomposing ASH by weight class, right? We're aggregating, we're showing DB time decomposed by weight class. And we do that because weight class is one of the dimensions that we capture in ASH. So we're doing a count star group by weight class, right? Down here, we have a top sessions list or top SQL list and a top sessions list, right? Well, we're basically decomposing ASH. In this case, it's ASH over the interval represented by this gray square, right? So this is a master detail chart where, we've highlighted on this area of the big chart. Why? Well, because we say, click on the big stuff. The big piece of color is the big DB time. That's where the performance opportunities are, or that's where the problem is usually. You see a giant hump of DB time like we see here, somebody had a problem right there, right? That all of a sudden database time spikes. Usually that's because performance has gone down the tubes. Database time is accumulating, but not more work is being done, right? So that's by definition, degradation in performance. Anyway, here we have top SQL and top sessions. And again, these are just, some group by queries on ASH. And here we're grouping by, first by SQL ID, but then within SQL ID by weight class. So we can see which of the, most expensive SQL and what were the actual weights and ratio of weights and CPU. CPU is always green. So here we can see this, there's only one guy, red, right? So some session is suffering a lot. He's in the red. It looks like application weights or concurrency weights, but everybody else, not so bad, right? But there's a lot of this light green stuff, which is scheduler weights. That means people are getting throttled by the resource manager. Same, same concept, slightly different, more recent version of the product. But again, the usage model, click on the big stuff, right? Figure out what are you interested in? Another thing to talk about here is that we always, when we break it down by weight class, which is the most common breakdown, especially for these activity charts, we always put CPU on the bottom, right? A lot of times people will sort of make an imitation of this. They'll do group by weight class, but they won't order the CPU. They won't order their weight classes so that CPU is on the bottom. Well, CPU needs to be on the bottom. Okay, there's no question about it. Why? Well, because CPU is the core resource. First of all, it's different from the weights, right? So it shouldn't just be in the middle of the weights as if it was just one of them. But more importantly, because it's subject to this limit, right? It has a hard limit, and we want to compare how much CPU is being used relative to the hard limit. Well, we can only do that in a stacked area chart. You can really only do that usefully with the bottom, with the thing at the bottom of the stack, right? Because otherwise, if CPU was in the middle of this sort of moving stacked area chart, it would be very hard to find out when it was approaching, the core count. Anyway, people get that wrong a surprisingly amount of the time. I guess it's not obvious, but Oh, I already answered that question. Okay, more Ash math, right? So this is sort of a newer version. This is Ash Analytics, which is kind of, sort of the successor to the perf page, and the top activity page is kind of using the active report technology that was introduced by SQL Monitor. But, it's very informative. Anybody, do we want to take a guess at what happened here? We can see a whole bunch of DB time here, and then it all kind of shrank. It looks like we, a lot less of IO, a lot less scheduler weight. I mean, a lot less CPU, a lot less scheduler weights. Now, we can see our core count down here, and we've actually got dark green above the core count, which is, pretty interesting. Looks like we're getting, a lot of hyper-threading advantage, maybe. But who knows, right? Looks to me like, a lot of application weights kind of disappeared, so what was that? Well, who knows, right? Maybe they, tuned a SQL that was holding locks too long, and, or added an index, and that improved the SQL performance of some SQL that was holding locks or getting locks. I don't know. But it's very telling. Something certainly happened to improve the situation from the left side of this chart to the right side. All right, I won't spend a lot of time on this, but this is the calculus of Ash math, right? And so if we graph active sessions over time as a function of time, then the area under the curve is actually the DB time, right? Well, if we project Ash samples into here, each of these stacks of dotted lines, each of these is an active session, every dot here, right? So when we actually sample, and they're separated by 1 second, right? So these represent Ash samples. Well, every Ash sample is kind of, you're actually taking a value of this function at a certain time, right? So we actually have values of the active session function every time we take an Ash sample, right? Well, what does that mean? Well, if we actually turn those into little rectangles like this, it starts to look like your calculus book from high school, right? And guess what? The width of the rectangle is exactly 1 second, right? So when we say count star, when we say add up the number of dots, right? We're really saying add up the number of dots multiplied by 1 second, and it gives you the area of all these rectangles, right? Well, what's the area of those rectangles is what we call a Riemann estimate of the integral, right? Of the DB time integral, because that's the area under the curve. So, when you do Ash math, you're really doing calculus. All right, multi-dimensional Ash math. So this is a feature that we introduced in Ash Analytics called the load map, right? And it was the original idea for tree maps in EM, but it got rejected the first time around, and then the second time around after the load map, the enterprise load map sort of broke the ice on tree maps, then we were able to do this. This allows you to basically analyze, slice and dice DB time using Ash dimensions according to your choice, right? And there's zillions of Ash dimensions. So how do you figure out how you want to break down, DB time? Well, you can break it down any which way to Sunday using this little tool. Now, that said, it can be a little bit of a challenge to figure out a good breakdown. But here, it's a multi-dimensional breakdown of DB time. Here, it's broken down first by weight class, then by weight event, then by SQL ID. So you can see, within weight class, which events were the most, and within those events, which SQL ID. So another Ash Analytics load map. Similar thing. I like this one. Basically, this one's broken down by weight event, and then SQL plan operation, and then object, right? And so, and this is focusing only on IO weights, right? So it's filtered to only show IO weights, and then within IO weights, that's a weight class. Within the IO weights, it's breaking down by weight event, by SQL plan operation, and by object. So it's actually relating the kind of IO that's being done, right? DB file sequential read, DB file scattered read, right? The kind of IO related to the optimizer decision that's causing that IO and the object on which that IO is occurring, right? So you're kind of mixing a physical object, you're breaking down DB time by combining elements of what's the actual thing, what kind of plan optimizer choice led to that thing, and then what kind of IO on that thing did that choice result in, right? So that's a pretty powerful thing. You're kind of going from, type of IO through, logical optimizer decisions, and then also down to the actual thing itself. Okay, man, we're really cooking here. This is great. So Ash Viz. So why do I get so worked up about Ash, right? So the reason is because since about 1995, I've been involved in this business. And when I say this business, I mean trying to develop and tools for DBAs mostly to understand and actually see what's happening in their database. I got into this biz, if you as I am calling it, with a company called Savant that I co-founded, and we basically wanted we wanted to help DBAs see what's going on. So Viz was a really important part of what we were trying to accomplish. The database between version 5 and version 7 had really gone a couple orders of magnitude in complexity, and so visualization seemed pretty important, and that's kind of what I've continued to work on at Oracle primarily. But there's just so much more to see in Ash, right? Ash to me is like a very high resolution video of what's happening in your database. And when I say high resolution, I mean, every second is pretty high resolution in the time dimension, but all of those other dimensions, it's almost like, you have a video of the actual scene, but you also have, thermometers, and you have other kind of sensors inside, that are taking track of all kinds of things about what's happening, right? And so what's really missing in my mind is really the channels, right? The viewers, right? There's all these video, it's this really dense video, and we have these tiny little viewports into it, right? And so I'm really interested in, trying to expand the number of viewports. And so that's what I call Ash Viz. I used to dream about something called Ash TV, right? You would just change the channel on the thing, and you would just sort of see Ash, different kind of aspects of Ash, on it, as if it was a TV channel that you could tune into. So what's this here? So these are basically all the weight events from a large four node, from an Ash dump from a large 4-node rack cluster running an OLTP application. And these are filtered out to only show cluster weights in red and IO weights in blue. And the y-axis is the log to the base 10 of the time weighted, right? So, higher up means longer time weighted for weight events, right? And the x-axis is just the time axis, right? This is when the Ash dump started, and this is when the Ash dump ended. And it covers 4 different instances, but in this case, we've mixed the data from all 4 instances. But you can see very clearly, that cluster weights, take approximately I always get this thing right. So this is a millisecond right here, right? 10 to the 3rd microsecond. So cluster weights a little bit above 1 millisecond, but during 2 little interrupt periods here, they went all the way up almost to 1 second, right? 10 to the 6th is 1 second, 10 to the 3rd is 1 millisecond. So big degradation in at least some large percentage of cluster weights during 2 incidents, let's call them here. The other thing we can see is IO weights have sort of 2 very strong bands, right? One around 10 to the 4th, or 10 milliseconds, and the other, and then this is, by the way, if you start saying haha, your IO sucks, this is from a 2004 Ash dump, okay? So you can't apply today's standards to the IO times here. And then, but there's also a clear band up here around, what, 10 to the, in the hundreds of milliseconds, right? Well, these are probably being served from the Unix cache, and these are probably, you know, by today's standards, slow, but the regular pace of IOs. Anyway, this is what I call a latency point cloud, right? We're showing every wait event in the whole ash scope. It's probably about 150,000 points. Going completely the opposite way, this is highly abstracted, but these are box and whisker charts of wait event latencies by wait event factored by wait class. So within the application wait class, there were 3 different events observed, and these are box and whisker charts, which are sort of a simple statistical mechanism for showing a rough sketch of the distribution of values, right? And so again, the x-axis is the log 10 of the time waited. We're looking at wait event latencies. A lot of my AshViz stuff is about wait event latency. But this is a very abstract characterization of ash. But you can see, oh, the 2 red lines are drawn at 1 second and 1 millisecond. So you can see most wait events happen between one millisecond and 1 second, but some not. Okay, these are violin plots of something we didn't talk about, which is using time weighted to actually estimate how often wait events occur. What do I mean by that? Well, if I sample a wait event in ash, if I just count the wait events in ash and say, well, this is the rate at which these wait events are happening, well, that's not quite true. Why is that? Well, it's because the sampler is biased in the time dimension to longer wait events. If a wait event takes 50 milliseconds, it's only 1/10 as likely to be sampled as one that takes 500 milliseconds, right? Because the ash sampler is going to wake up whenever it wakes up. So the guy that's out there longer has a higher probability of being sampled, right? And so, but it turns out that you can actually estimate the wait event counts from ash samples. In other words, you can sort of undo the bias, right? And so what I'm doing here is comparing the sampled events, the distribution of sampled event latencies, again, log 10 of time weighted, with the estimated actual density of occurrences, right? So you can see that even though we didn't sample that many of these low latency events, the fact that they were very low latency and the fact that it's very unlikely to sample them because they're low latency means that our estimate of how often they occur is much higher than how many times we sample them, right? So you can see that the graph on the left is kind of like squished to the downside from the graph on the right, because that's how you undo the bias. That's the effect of undoing bias. All right, I'm almost done here, but this one's pretty cool. So this is basically a mapping of, again, all of the ash samples mapped to a 2-dimensional. Basically, what we're doing here is every point on this chart represents a SQL ID executed by a session. Okay, so we're mapping sessions to SQLs. Who's running what SQLs and what SQLs are running by what sessions, right? Now, we don't know which sessions they are or which SQLs they are, but that's not the point. We're looking for patterns here, right? And so basically, you know, radial lines in this chart, the radius is the session axis, right? And the arc, the angle, is the SQL axis, right? Is the SQL, right? So every line is basically a SQL ID that's executed by a lot of sessions, right? And every circle that goes around like that is a session that's running a lot of SQLs, right? And so it's interesting, you know, and then they're colored by the type of command, right? So blue is select, green is PL SQL execute, red is insert, white is sort of unknown. I think it might have, I think white, oh no, delete is yellow. So you can see, and then the size of the bubble, I failed to mention that. The size of the bubble is the amount of DB time. The size of the bubble is count star, right? So this is really a graph of, you know, ash count star group by SQL ID and session ID, and then rendered in this sort of polar coordinates fashion. But it's pretty cool. Now the SQL IDs are sort of randomized in the session ID, so there's no ordering at all. But if we want, we can actually put some order on those things, like, separate them out by SQL, by type of SQL, and then actually put the heavy ones to the outside. The problem with a graph like this is you don't really know what's going on in the center, right? You can really see things out here, but once you get down to about here, you can't see. But if we actually order things, so this is basically putting the most expensive to the outside so they can see them, we kind of get something like that. All right, that's it. We made it. Anybody got a question?
There's been numerous questions, John, but I've been answering them.
Oh no.
But that's okay. I had many questions, but like I think we can all pretty much say that it's a measure of 30 years of IT experience that you can go through such a volume of data and of content for us and still come in literally, to the minute, bang on time. That's very impressive. I have a question which, and this may be total fiction, but there's a story that goes around back in the Oracle 7 days that the whole reason the weight interface, all that instrumentation was added into version 7. There's a story that goes around that some big benchmark went absolutely belly up, and then there was this urgent rush to slam all this stuff in so it could actually be worked out. Is this true, or is this an apocryphal story? Was it always planned that this stuff?
I don't know if it's true or not. I can ask Graham. Graham would know. I've also heard things about, the big project that James and some other folks worked on at that time. Oh, geez, somebody on this list.
Was that Europe car? The big rental?
Yeah, Europe. Right. So that was a huge, and I think that was a big OLTP system. And I think, there was a lot of kind of ad hoc stuff done there too, right? So there might have been a connection with the Europe car thing too. But no, I don't know. I can't confirm or deny the apocryphal story about benchmarking. But back in those days, benchmarking, it was really important, right? And so, people don't really seem to take it that seriously anymore. Or at least that doesn't seem to be the case. In my, what do I know? I'm so out of touch with the real market, but it was a big deal back then.
I have to give a shout out to all the attendees, because we were sitting at about mid 60s, and then John started talking about derivatives, integrals, and calculus, and the number stayed the same. I was very, I thought it would just like kasprunk, we'd absolutely crash. But
yeah, we didn't do any statistics, right?
Oh dear. So
it's nice to know that your calculus actually does something, right? I mean, when I kind of realized that, and it's not like it's like some great realization, but when we were counting ash samples and sort of equating it to dB time, sure, that sounds about right? But then it's kind of like really realizing that counting ash samples is really drawing that little Riemann integral thing underneath your to estimate dB time. It's like, oh, okay, that's why it works.
You mentioned before that M-Monlight goes and looks at all these session state objects. Is that why whenever we have an Aura 600 or a 745 and we get this giant trace file, is that the meaning of all those SOs that you see in the trace files as session SO this, SO that? Are they state objects that are being dumped?
Probably. I don't know. I'm not really a trace file, dump file guy. I kind of stay up. I'm serious, I'm not really at that deep level. There's a whole cottage industry of that, as you know, but it's not really. I kind of like the viz stuff and assembling pictures of things a little bit.
Okay. Here's a question for you, John.
The geeks like flame graphs, and flame graphs are cool too. So they're geeky viz. But
here's one that's coming from Mark. Would a daily comparison of dB block changes versus dB time over a period of time be a fair trend indicator of dB performance, or are there other variables to be considered?
dB block changes?
Yeah, versus dB time.
Well, I can accumulate a lot of DB time without changing any blocks, right? I mean, that's a query, right? So I don't know. I'm not sure that block changes to DB time. I mean, again, you could try to relate lots of things to sort of movements in DB time as, potential explanatory things. But, I mean, to me, it's always sort of slice and dice ash data to try and figure out what's happening. And,
Yeah, just my thoughts on that, Mark, is I would say if you had a steady state, say, transactional system, where like an OLTP, where the core thing that you're interested in is transaction throughput, then DB block changes is very relevant to that. So, as DB block changes, if that doesn't change, but DB time goes up, then it means you've got a scalability risk for your OLTP system. But as John said, there's a whole lot of systems out there where literally the amount of changes you make to the database is maybe 2% and reads are 98%. So very much depends on your use case, but certainly I could see that being useful in something where you've got a steady state system already that's doing a fixed amount of transaction work and your DB time continues to grow, for example. That would be something that says, well, we're going to hit some issue here in the future because we're doing the same work for more and more DB time. So.
Hey, I see Doug Burns is on there wisecracking. So this actually made me think of something that I want to mention. I don't know how much time we have, but something I'm very interested in that's a little bit maybe relevant to Mark's question is that, we tend to think of like a lot of these database metrics. Let's talk about DB block changes or any of those things from sysstats, right? We usually look at those on a per transaction basis or per second basis, right? And what I'm really interested in and haven't really done any much work in, but I think it's very useful is, don't normalize those per second, normalize those per second of DB CPU, right? This is how much bang I'm getting for my CPU bucks. CPU are the bucks you're spending, right? DB block changes are what you're getting out of it, right? So measure the rate, measure block changes per second of DB CPU time and see if that changes, right? If you normally, if your system, as Connor described, if your system is normally, transactionally stable, it's doing a lot of block changes, it's using a lot of CPU, you should have a very steady rate of block changes per unit of DB CPU, right? And if that changes, then, something happened. Your transaction got more expensive, right? Somebody put more code path. Now I'm taking twice as much CPU per block change, right? So that is a very interesting avenue. I would say, daily comparison of DB block changes per second of DB CPU, which is a component of DB time, the one that's doing work, right? That would be a very interesting thing. And not just a daily comparison, but, on an hourly, like every AWR snapshot. So, one of the things I want to do is sort of write some queries on AWR, and we'll just do that normalization by DB CPU and look for precisely those kind of things. So great question. Sorry, it took me a while to get the right answer.
Okay, we're out of time, John. We're going to wrap it up there.
Hey,
but
good.
I two things I want to say is, number one, thank you so much for your time and for your massive, vast amount of information. That's awesome for me and the attendees. And the second thing I will say is to the attendees, this is my 37th, I think, office hours. So if you're sick and tired of just Connor talking all the time and you prefer these things where I'll go out and try and get some more guests, please hit me up on Twitter, send me a message saying, yeah, Connor, we're sick of your crap. Go get some more interesting people and we'll do that. Or you can say, hey, Connor, just keep it to yourself. I don't mind either way. Our job, myself, John, our job here is to serve the community and obviously to make you more and more successful with the Oracle database. So having said that, thank you very much, John, for your time. Thank you very much. It's very early in the morning for John. And yeah, we'll see you in a month's time for the next office hours. Okay, so
yeah, no, I mean, ask me back. I'm happy to come. It's great.
Fantastic. Thanks everyone for your time, and we'll see you next month.